I'm a software engineer here at the Flatiron Institute in SEC. I mostly focus on high-performance computing, though I kind of help whoever with whatever. So there's a lot of Python and Julia. And I guess I've kind of become the informal micro benchmarker for the Institute, while Giraud in SEC is more of the macro benchmarker. But we have two people who work very hard to try to tell people how to configure your software to run best on the cluster. And so I am going to do my best to make a talk about measuring the speed of things interesting. We'll see how that works out. So let's talk a bit about BLAS and LPACK. Most of you have probably heard of it. If you have not, BLAS stands for Basic Linear Algebra Subprograms. And LPACK stands for Linear Algebra Package. So a little bit about BLAS. BLAS is just a set of linear algebra routines, really. It just does anything that you might want to do with a matrix, vector, or scalar. So it has a very standardized implementation, so you can kind of swap them out. There's actually tons of implementations to do these operations. And they operate on real complex float and double, and there's extensions to do mixed precisions and all these other things, but the classic BLAS is float, double, complex float, complex double. It's broken into 3 distinct levels, which were actually published at separate times. Level 1 BLAS is scalars and vectors and scalar vector operations, things that you probably don't ever need to actually use BLAS for nowadays. 2 is matrix vector operations, largely, what's a matrix times a vector. And 3 is matrix-matrix operations, which is matrix times matrix is what most people will use it for. There are other routines in these, but these are the ones you actually see, and you might actually be using some of these under the hood when you use something like these higher level routines. So a bit of a brief history. So BLAS was first introduced in 1979, but only level 1 BLAS. And it kind of was born to increase, with their stated goal to increase portability and efficiency. So at this time, we did not have the vast internet with all these libraries gluing everything together. People would share things, or these libraries would be given to you by, say, the computer manufacturer. So IBM had their own linear algebra routines. I forget the name of it. And you would end up writing your own sorts of things to do linear algebra. And now it's kind of common sort of pressure on engineers to use other people's code because they probably did it better than you. And it was in Fortran. Fortran 77, since this is 1979, but also the Fortran 70 bindings. It came with 38 packages. And then later on, in 1988, we got level 2. That's the vector operations. And in 1990, finally, we got matrix multiplies, which is quite a long time to wait for a standard interface for matrix multiply. Since Fortran was invented in, like 1956. So this is all grabbed from the technical documentation, which is on Netlib, which is the reference BLAS implementation. It is a 315-page document of just what all these routines are and how to implement them. I did not read the whole thing for this talk, just kind of grazed the intro. LPACK, I don't know the history of. I didn't have time to build it, but it's basically everything else you might want to do with linear algebra. Decompositions, largely, I think, is what most people use it for. QR, LU, eigenvalue, SVDs, Choleskis, LQ, QLs. There's actually a few others. Things I don't actually know that much about. I am not an applied mathematician. I am a lowly computer engineer. Also, least squares calculations and some rotations and things. Basically, if you want to solve AX equals B, quite possibly under the hood, if you're using something like Python, it's going to be doing one of these things. So this is a huge landscape to do linear algebra on computers. Not all of these are BLAS and LPACK. There's other implementations to do similar things. So Netlib is the one that Jack Dongara and co. work on, is the reference implementation. the one I was just talking about. I'll, in the talk, either refer to it as netlib or just BLAS. Then there's MKL, math kernel library from Intel, OpenBLAS, which is the open source version of an extension of GoToBLAS, which was like the fastest one 20 years ago. Bliss, which is some up and newcomer. Atlas, which is an old way to do things that doesn't seem to work most of the time. I couldn't get it to compile for this talk in time, so I gave up. Atlas measures things on your computers to try to build the fastest way to do things. It is not the fastest anymore, so it's not worth messing with. And there's other implementations for Black, like FWAM, that also are not in this talk. There's sort of BLAS implementations. So for C++, there's Eigen, which is a completely template-based library to do this. It is actually fairly performant, which I'll show in the talk, but it adds orders of magnitude to your compile time often. So just be wary when you use it, and sometimes the syntax can be a little meh because it's a template language. There's also Armadillo. I didn't try it for this talk because it's not BLAS. I made a BLAS interface for Eigen. Trilonos for distributed MPI. I assume that Jenny will talk about this in the distributed version of linear algebra. I will not be talking about it. There's other things like PETSI. And then there's Accelerate, which is some Apple-blended BLAS and LPAC, also not tested for this because we do not have a Apple cluster. There's a ton more. These are sort of closer to the state of the art or just more common. So for benchmarking, as usual, benchmarking is sort of a combinatoric nightmare, and this is one of the worst I've ever encountered. So there's a lot of routines that people actually use and care about. GEMV. Gem is general matrix multiply. GEMV is matrix vector multiply. GETRF or GETRF is triangular factorization. That's for LU decomposition. SVD is SVD. Eigenvalues and something else. I only ended up doing 3 of these. I'll talk to you about that in a bit. We have 3 types of nodes. There are tons of implementations, 10 listed here. 4 precisions, up to 64 different threads, 3 different OpenMPs. How big of the problem size do you care about benchmarking? 15-ish, maybe, which comes to about 20 million measurements. I did not want to try to make that many or collate that many measurements, and turning that into something condensed and usable is completely impossible. I don't want to have a machine learning model just to parse my output. So I settled on 3 routines. I still have to keep the 3 nodes. 6 basic implementations. I still did all the precisions. Powers of 2 on the threading. 1 OpenMP. So everything in this project is done with GCC, which largely won't matter because these are library calls. So it really matters what the library was built with, and all our libraries are built with GCC. And about 16 problems per function, which reduced my combinatoric nightmare to 24,000 measurements, which is tractable. I didn't end up using all of them, thankfully. So there's a lot of issues with benchmarking. Micro benchmarks are hard, so if something doesn't take a lot of time, it's very hard to get an accurate timing for it. There are libraries that do this much better than any of us can without a lot of extra work. So I'm using the NanoBench one, which I'll mention in a second. There's a lot of implementations. Linking different implementations means I need to detect the implementation, link it in, build a program with that version, and then do that for each of my implementations, which is annoying. Eigen doesn't provide a BLAS interface by default, so I had to make one. But Eigen is so popular and is reasonably fast that I decided it was worth doing. We do not have netlib, Atlas, or Bliss on the cluster. Netlib and Atlas are intentionally removed from the machines so that people don't link against them because they're so slow. And some implementations don't use CPU dispatch, which means I need to build them local to the machines. So I did use NanoBench. I wrote some implementations for what not to do, and then Eigen, and then just used some CMake magic and linked against FlexiBLAS, which we use on the cluster, and it is a godsend. FlexiBLAS allows you to swap out your linear algebra BLAS LPAC implementation on the fly. You provide it a path to a shared object that contains your implementation, and it will swap out for that, use that implementation at runtime. So I don't have to compile. I compile one program, and I can run it on everything.
So, Robert, is that a in-house
No, this was developed by a German group, I believe. We do use it. So our Python and anything linked against BLAS in the module system actually already uses FlexiBLAS. So if you load OpenBLAS or OpenBLAS threaded or MKL, it will use that under the hood automatically without having to swap any modules out. It says the source is here. I have not actually uploaded the source yet. It's private. Y'all can't know my shame. So I will talk about the 3 routines I did, and why part of this talk is why you should not implement linear algebra routines yourself. And so the first one I want to look at is GEMV, which is the general matrix vector multiply. And it has a simple form. Not usually what I think of as a matrix multiply because there is, or a matrix vector multiply because there's a scaling factor on the output and on the input. But this is the general form. I have a pointer. Yeah, I guess I should just use the big wand. Y is equal to alpha, some scaling factor, plus beta times itself. So y plus equals beta times itself. And this is just a matrix vector multiply. That's it. This is an order n squared algorithm because I have to do this for each I. All my matrices I work on are square in this problem because I did not want to think about adding another dimension to my combinatoric nightmare. So this algorithm is what we call n squared.
Is that an assignment or an algebraic assertion?
Either. I don't understand the distinction in this case.
I mean, are you assigning a new y?
Yeah, yi, for each I in my output vector, I'm assigning it a new value.
So you're not solving for y's?
No, there's no solving here. This is just, it's just a, just a direct assignment. That's all this routine does. This is the interface for that, which is annoying. When you think about multiplying a matrix and a vector, you don't usually think about, I don't know, what, 5, 10, 11 parameters or something. But it is general, so it allows you to work on, say, matrices that are not contiguous in memory. They have strides and things like that, and same with vectors. And I even, usually you want to work with dense stuff, but this, in their infinite wisdom, they gave you the flexibility to work on data that was not contiguous in various ways. Also, it's Fortran, and I've written it in C interface style, and it always has to have this underscore because it's calling a Fortran routine. Anyway, it's quite a lot. I used to hate the GEM interface or the BLAS interface. It's hideous, it's old, but also they wrote an interface that has been in use for 45 years now, so I've changed my mind. They had a lot of foresight. They're brilliant predecessors to us, and we all should be grateful to the inventors of BLAS. So let's do a quick, naive implementation of BLAS, or of GEMV. I have taken a lot of the cruft out just to make it straightforward. There's no strides. So let's make a dGEMV for doubles, and it just loops over I, multiplies y times the scaling factor, and then adds the matrix multiply elements. So this is an m by n matrix, m times n amount of work. And now, just note, this is not actually a good implementation. Don't do this. And here's why. So I'm sorry that this is so dense. Like I said, 24,000 measurements. All my plots won't be like this, but quite a few of them will. The important things to take away is look at blue, OpenBLAS. Always quite good. EigenBLAS, actually very good here, which is kind of surprising because it's not optimized. It's just done on the fly, except when you do complexes, when suddenly OpenBLAS is just light years ahead of everybody for no apparent reason. This is just on ROMs, though, because it changes every freaking time. Benchmarking is annoying. MKL does fine, but it's just because OpenBLAS does so well.
You're showing this as a ratio to something.
The ratio to the reference implementation. Sorry, I broke the golden rule. Explain what my plot is. All of these are, each of these are divided by the reference implementation, which I have, is in red. The red line will always be 1. And it's because everything else is divided by the reference implementation. So this is the amount you're faster than the netlib implementation, which is the one we tell people not to use. And you see why is because most of the others are 4 to 10 times faster.
Sorry, is the netlib the same as the naive loop you just showed us?
The netlib is a improved version of the naive loop, but it's not using vector instructions. It's relying completely on the compiler to do what it needs to do.
But then you give it O3 or something.
Yeah, these are all compiled with like O3, basically.
Okay.
Yeah. I will kind of cursedly go over these and tell you roughly what the weird takeaways are. Once again, Ice Lake, for some reason, Eigen is doing extremely well, which is weird. I just can't explain what it doesn't usually do so well in things. But it's competitive with like state-of-the-art implementations of this routine. And once again, for complexes, OpenBlast is just crushing it. So if you're using complex numbers and you're doing a GemV, and that's the only thing you're bottlenecked by, which is never the case, use OpenBlast. And you see very similar results on the Genoas, except OpenBlast is a little more. Well, no, once again, on complex, I do not understand what they're doing. There's a few cases in this talk where OpenBlast is, for no apparent reason, 8 times faster on very weird routines. This is kind of the interesting one, and I'm sorry that it's flat. It's because GemV does not, this is about multi-threading, so each of these is actually now the number of threads. The imaginary line would be ideal scaling, this sort of transparent one. And you see that GemV scales very poorly compared to what it should be doing. So in short, don't use threads. They're real bad. You're just wasting lots of compute power for no reason. It's just spinning, doing nothing. My general recommendation will be always use less than 8 threads. This is a very lightweight problem. It is not ideal for threads. This plot is just to show you that don't use threads with small problems, because this takes order less than a microsecond. And so trying to split that among 32 units is just, you spend more time making threads than you actually do using them. Though for some reason, OpenBlast and MKL actually scale on Ice Lakes, and I don't understand. So, Jim. Oh, that's sad. Yes. Please use the C mic.
Slide.
Yeah.
Am I correct that the Ice Lake is an Intel node and MKL is developed by Intel, while ROM
Yes.
and Genoa are AMD?
Yes, but OpenBlast also does well. And it does it on Genoa. The thing that Genoa and Ice Lakes have in common is AVX 512, so I suspect they've both written an AVX 512 implementation and just didn't bother with a good AVX 2 implementation. Because Rome does not have the same instruction set as these two nodes. It is using an older one that can work on smaller vector units. So I'm not going to talk about SIMD in this talk because I don't have time. So Gem is the same problem, but with a matrix on the right. So now you're doing a matrix multiply. I don't know why it's all the way over there. It wasn't earlier in the day. And a similarly annoying interface that also got chopped off like it didn't earlier. So it's an order n cubed algorithm because each element has n squared work. So, or n work, and there's n squared elements. So n cubed work. This would be a basic implementation, same as before. Loop over I, J, and L in this case, where K is my third index. So M times N times K work, so N cubed. I didn't really talk about it, but also if you notice, there's a MyBlast, this purple line. And you see down, as you get to big problem sizes, it's actually slower than the reference implementation. Don't do it. there's things that are literally 100 times faster than what you can do. Similar to before, except now there's this newcomer Bliss that seems to perform well whenever there's a very big matrix. And big in this context is relative. Some people view big as like 1,000,000 by 1,000,000. Here, to me, big is 1,000 by 1,000, so about 1,000,000 elements. The key kind of takeaway is OpenBLAS still the best. Just use OpenBLAS on the ROMs. On Ice Lakes, it gets a little murkier. Ice Lake is an Intel machine. It's made by Intel. They make MKL as well, so they optimize for it. So you see that MKL actually performs better. So you got Eigen is actually still competitive, factor of 2. But MKL just crushes on the Ice Lake nodes, like 30% faster in some cases. And I'll have a little flow chart for how to decide which MKL or BLAS to use, because none of the others are ever really worth it if you're really optimizing for speed. Genoa's OpenBLAS crushes, like not really a contest except down in the complex land where suddenly Eigen is the best. I don't know. But they're all about the same, so it really doesn't matter on the Genoas for complex, and OpenBLAS is just a general good all around. This is all for single thread stuff. For scaling, you see that actually you start getting very, I know it's very tiny. Logarithmic scale was very confusing, so I opted for something where you can't really tell what's going on. But essentially, up to 4 threads, OpenBLAS and Bliss and MKL all perform pretty admirably. This is on a problem size of 1,000 by 1,000 matrix. And that's on Rome. You actually get better scaling on the Ice Lakes and on the Genoas, but for most of the time, up to 4 or 8 threads will give you very close to ideal performance if you're using big matrices. The bigger your matrix, the more threads you'll get ideal performance out of. This is sort of just a rough guideline. Most people are not working on matrices that are bigger than 1,000, I don't think. And if you're working on a smaller, use less threads. Yeah.
We want to use matrices as big as possible often. Like sometimes it's...
How big?
Sometimes RAM is the limit. Like you'll factorize a 50,000 size matrix and spend an hour on it.
Oh.
I mean, we do things like that.
Well, good news. We're talking about factorization next.
All right.
So at least for LU decomposition, I did not do SVD and QR. I have limited space and time and sanity. So LU decomposition just stands for lower upper. You break your matrix into an upper part and a lower part, a lower triangular and upper triangular, and you say, I'm solving the equation such that my pivot matrix, or times A, my matrix I care about, is equal to some LU decomposition of those matrices. This is called partial pivoting LU decomposition. Wikipedia claims it should be order n cubed. Actually, my measurements showed it's order n to the 2.4, which is strikingly close to Strawson's algorithm. So it should be the time of matrix multiply, but I sincerely doubt that's what they're doing, so I'm very confused. But benchmarking is hard. And maybe I'm just not getting up to problems that are big enough to actually see the n cubed scaling that it should have. Yes, Alex? You have your finger on that.
Sort of like, oh, cache.
Yes. Yes. Oddly enough, doing an LU decomposition, way simpler interface than anything else. So whatever, it's because it does it in place. You don't have an output matrix. It just takes your matrix and trashes it. I don't care about you. So once again, OpenBLAS, MKL for small ones, OpenBLAS for big ones. This is also not the OpenBLAS we have in the cluster. It's 0.02 versions ahead, but we'll be introducing this on the cluster in the next couple of months probably. Ice Lake, MKL. Intel machines like MKL, Everything else likes OpenBlast, but OpenBlast performs competitively. Bliss and everything else kind of suck in comparison. And I did not implement my own version of LU decomposition. I've done it before. It's annoying. And Genoa, OpenBlast. That's really what you should take away. OpenBlast, still amazing. If you really want to stare at all these plots at some point, they will be available. I can share all the code. You can benchmark it on any problem you want. Not surprisingly, LU decomposition scales even worse than everything else, and it's because it's not an inherently parallelizable problem. It's an iterative problem. You start at the top row, and you just you start removing elements row by row, which makes it very, very, very hard to parallelize efficiently. I suspect some very smart people have worked very hard to get these kinds of numbers where it gets 50% scaling efficiency up to 4 threads or 8 threads. But once again, use Icelake for MKL and OpenBlast on everything else. So my conclusions for single-threaded, I have made a very simple flowchart. Which node am I using? If it's an Icelake, am I using decomposition? Yes, then do MKL. Otherwise, OpenBlast is a fine choice. MKL is also a fine choice. Everything else, just use OpenBlast. It's just the best. It's not a contest. And for multi-threaded, for efficiency, unless your problems are really huge, like Alex's, like we do an hour-long LU decomposition, just use like 4 threads or less. You'll get the most efficiency out of the system. Use OpenBlast, broken record. For large numbers of threads, they favor MKL and Bliss and not OpenBlast. OpenBlast still has an issue with threading. I don't know if that can be resolved. I actually kind of want to play with that because they have various threading options, but I haven't gotten to it. LU decomposition and GemV usually scale poorly unless you're on Icelake and with MKL. So if you have to factor a big matrix and you really don't want to spend a lot of time, use MKL on Icelake. But otherwise, don't bother. We have some various tips for using blasts at Flatiron, just core takeaways. The single-threaded OpenBlast doesn't actually, the default OpenBlast at the Institute only uses 1 thread by default, so you'll automatically get sort of the best performance. If you need to make things slightly faster, you can load the OpenBlast threaded module or the Intel 1OPI MKL module, and they'll switch out that module for you magically if you're using something like Python or any of the modules that use Blast under the hood. You do need to set OpenMP num threads accordingly because by default, these things will use all the threads available to them, which, like I showed, the scaling is very, very bad with large numbers of thread. And actually, in some cases, you get worse performance with more threads. And so you really, actually, if you do load one of these 2 threaded modules and you want to do them, make sure that you look at your number of threads and set them accordingly. MKL also has the MKL num threads to specify it without adjusting the OpenMP num threads. In Jupyter Notebooks, since you often allocate 4 cores anyway, you might as well set the number of threads equal to 4 in most cases. There's this neat little library called threadpoolctl, which will allow you for certain routines to use more threads or less threads inside a block in Python. I use it all the time. It's amazing. It can save you a lot of time and give you a lot of performance by controlling it. If you're compiling your code, try linking against FlexiBlast. There's not really any performance overhead costs for linking against that and having it load in the blast for you because most of the time is spent doing the math. There are some caveats with MKL. I don't want to get too deep into them. You can shoot yourself in the foot if you're using threaded blasts by having n processes, like the number of processes available to you as the number of cores, and then each of those are spawning n processes threads, in which case you have an n-squared threading problem, and it oversubscribes the CPU, and your performance just absolutely tanks. This is actually why we changed the OpenBlast module to single-threaded, is because it was so often a problem that the threading was actually causing codes to run slower that we just turned it off. But you can, like I said, switch this out if you deeply care. MKL num threads, like I mentioned, can save you if you're using MKL. MKL uses, via FlexiBash uses the MKL, I don't know what the RT stands for. I can't remember. Real time. That's a silly name. This can have issues with OpenMP thread nesting and lots of other issues. It does all kinds of fancy things under the hood to select which implementations to use. And if it's using threading, you have to make sure that it's working properly with your threading. Our MKM module handles some of that stuff, but sometimes you want to use like sequential threading. So if you nest your BLAS calls inside of OpenMP threads, it can be, the MKL RT library can cause problems. And so you need to make sure to set the right environment variables. I don't remember what they are. I didn't have time to build them for this talk.
Can I ask a
Yeah.
sort of user question again? Like,
Yeah.
Let's say you've discovered that it maxes out at 4 threads, but you have 64 available. You run, I don't know, 64 cores or something. You can't really do anything with the rest of the machine. Is that right? Because BLAS is using the full RAM bandwidth.
Yeah.
Is that, it's sort of like...
It's not using the full RAM bandwidth because you have the NUMA domains, which control bandwidth from different chunks of memory.
Yeah.
So you can keep it local to 1, and that would be, actually, that's usually preferable. I'm not going to talk in depth about that, but which processor your code lives on deeply affects its performance when you're doing multi-threading. So you can usually run on different NUMA domains and not suffer that much of a performance penalty. The Rome nodes and the Genoa nodes have historically had this problem where you can max out the memory bandwidth, but that's usually when you're well over half the machine's capacity when that starts happening. So you can run multiple copies of the code with 6 copies of the code with 4 threads apiece and still get very good performance. And this way you're using half the machine or more. There's a bunch of things I wish I could cover. Linear algebra is a very big problem space. There's sparse problems, distributed memory. Jenny's talk should be covering some of this at 12:15. She didn't have a blurb, but I just assumed, given the title. I didn't give a chance to do GPUs, but there's really only one library. There's 2, but use cuBLAS. If you're using AMD has a version of cuBLAS themselves. I don't remember the name of it. I also didn't talk about threading and hybrid codes, which is a common problem.
ROC.
Huh?
ROC.
Yeah, ROC. ROC-M or whatever, yeah. That's the name of the library. It's just, they just call it ROC. That's funny. All right. Oh, it says ROC-BLAS. Yes, like most things. Replace cu with ROC. But we only have a couple of AMD test machines here, so it's not that relevant to the work here. But if you're writing portable code that runs on multiple interfaces, you do need to consider that. But by using a standard interface, you do allow yourselves to swap them out in the future. And the cuBLAS and the ROC-BLAS interfaces are compatible with one another. There's like a AMD tool that allows you to switch between them. So that's it for BLAS and LPAC. Let's move on over to FFTs. Yes, what's up?
I just wanted to put in a little piece that you didn't put in, that of course you know. The BLAS-1 was developed as part of the LinPack project, which was linear solvers in the late 70s.
Yeah.
And BLAS-2 and 3 were developed as part of LAPAC, which is linear solvers and eigensolvers and everything in the late 80s. And the key thing to understand is that's why BLAS-1, 2, and 3 look like they look like. They're basically the underlying toolkit that runs those 2 packages.
Right.
And if you were designing it, say, for general computations, you might have additional functionality, different functionality, and so forth. But that's why the BLAS-3 has these funny calling sequences, because they fit perfect inside the algorithms that are used by LAPAC.
Thanks for that. Jason.
Okay, this might be a little too technical, my own problem, but suppose I have a problem where I have matrices of multiple sizes, right? And I want to do matrix products or something. But if I choose, some number of threads, it's right for the matrices of one size and not for the other. Is there any solution to this besides me chunking things up myself?
In Python, it's fairly trivial to use this thread pool CTL, which will set the number of threads specific for that matrix.
I see.
In C++, it depends on if you're using OpenMP or MKL directly or FlexiBlast, but there are ways to set the number of threads temporarily and then unset them when you're done.
Okay, but is there
that's
a way
manual
to have,
intervention from the coder, yeah.
Okay, that I have to decide.
That said, most of these algorithms, especially MKL, try to be pretty smart about when it should use threads and when it shouldn't, and if the problem size is too small, it just won't, which is why some of those have better scaling than others.
I see. So there is some intelligence where
There's
threading gets
a
shut.
modicum of intelligence. I have no idea how it works under the hood, but it seems to be pretty heuristic.
Okay, thanks.
Which makes sense because it needs to be fast. It can't measure things.
Right.
Okay. Like I said, I'm going to talk a bit about FFTs. Oh, hello, one more.
You mentioned Python that you will switch the module and change the implementation that NumPy is calling. Do you have any clue if you can change this in Julia?
If Julia is linked against FlexiBlast, it does not work. At least yet. Okay, thank you, Dylan.
Julia has its own BLAS trampoline.
Yeah.
So you can change BLAS in which the Julia interface using linearalgebra.BLAS.
Thank you. It makes sense that Julia would have a solution to this problem because it's really important to Julia. Okay, so let's talk about FFTs. I am by no means an expert on FFTs. I have crammed for this talk the best I can to understand them as best as I could. So everything, one has an asterisk for periodic functions, and it has another hidden asterisk for I don't know what I'm talking about. And so if I say something silly, I hope that Alex or some other expert will help me out. So what is a fast Fourier transform? What's a Fourier transform? It's a magic algorithm. It's incredibly simple, and it has completely shaped basically almost every field in the 20th century and continuing into the 21st. So in places diverse as electronic music and audio signal processing, image processing, including MRIs. Actually, a very important piece of MRIs, which is part of my work with Alex on FNUFT, the non-uniform FFTs. Solving PDEs, and anything where you care about the frequency of things, and sometimes when you don't and you just want a cute trick to solve a complicated problem quickly. A lot of the 20th century was shoehorning your problem into an FFT because they are so fast. That really was. It's kind of crazy what you can do with them. So I'm going to define it real quick. So we have some set of sample points uniformly spaced. So like, let's say we're sampling the function sine of x, and you say x at x equals 0, 0.1, 0.2. That's what these xj's are, and then the height of them is the value of the function at that time. So you're basically sampling some function x, and you define the Fourier transform of this times this funny little omega j to the jkth power, or also jk. You can define it either way because they're exponentials. Any simple function or whatever. So this omega jk is just defined as e to the 2 jk, j times k times pi, times the imaginary, because I capitalized, looks weird to me, divided by n. That's it. It's just a sine and a cosine. Magic. This is, if you look at it not so hard, you see that this is actually just a matrix vector product, and it's an order n squared algorithm by default. This is not the fast Fourier transform. This is just a Fourier transform. This O(n) squared is a problem. It doesn't actually help you speed things up. It actually can slow things down sometimes, but naively, a Fourier transform is just a matrix vector multiply with a very easy to define matrix. You just calculate a bunch of complex exponentials and you're done. So to show how simple an FFT is, I wrote a very simple piece of code. There's a list of frequencies I call f's, some number of sample points, 400 here. I make a linear space from 0 to 1. I sum up all my signs. So this is just a sine of 5, 10, 20, 40 frequencies. I make a Fourier matrix, which is this one line of code. And then I do this FFT shift to make things nice and plottable because of the frequencies do this weird looping thing that you need to shift for. And there, Fourier transform, y hat, fm at y. Just do a matrix multiply. And you come up with something like this. Notice that 40, 20, 10, 5, there's a frequency at each of them. There's negative frequencies because Fourier transform is complex, and there's essentially a complex and imaginary part that end up coming out that you have to sum. So this is a set of these are the real values of the Fourier transform. Doesn't matter. It magically will dump out the frequencies of your waves. That's sort of the magic of the FFT. The real magic of the FFT is that convolutions in frequency space are point multiplications, while their integrals are sums in real space. So if you needed to do an integral in real space, it would be, or a convolution, it would be an n-squared algorithm anyway, and this can turn it into an n log n algorithm. And it's because while you have to do in real space this convolution x convoluted with y, the jth element, you have to do this sum over this. In frequency space, you just multiply the things. That's it. So it's almost always faster if you have an FFT, if you want to convolve two things, to just compute the two things in frequency space, multiply them, and then inverse transform them back into real space. And you can do that in n log n time rather than n squared. So the second you have more than, I measured in Python about 40 points, you're done. So for pretty much every problem that you want to do a convolution on, an FFT will just dominate. It's way faster. So I didn't describe what a fast Fourier transform is. It is literally any algorithm that does the same problem and faster than n squared. Most of them claim that, at least in best case, they're order n log n. No one has found a proof that you can't make one faster, but you probably can't make one faster. But they scale from n log n to n squared, which I'll show. The FFT, like everything, was invented by Gauss in an unpublished work, interpolating asteroid objects from equally spaced observations. Uniform things, he got a frequency thing. He didn't want to, I guess, calculate n squared problem, so he came up with something where he basically he realized that you can split it into two smaller sets of Fourier transforms, and you could just do this recursively. Another one came up in 1932, the interaction algorithm for Hadamard and Walsh transforms. This is apparently a thing in statistics. I'm not a statistician. I have no idea what any of these things are. 1942, Danielson and Lanczos, DFTs for crystallography, which is the most natural space for an FFT. And then in 1965, the algorithm that everyone knows and loves and is underpinning most of the FFT implementations in some form or another, Cooley and Tukey detecting nuclear tests, actually, from the Soviets. They apparently came up this in a meeting with the president. Or also periodicities of spin orientations, like most scientists, they're like, well, I can use it for, things you care about, but I really care about this really obtuse thing. This is all taken from a very cute little paper. What is it? Not your family's, or the whole family can use? Yes, an algorithm the whole family can use, the FFT. It's a short read. It's quite nice. It will cover this much better than I can in this short amount of time. But the basic idea for the FFT algorithm, this is if your problem size is n, you want to transform n points, and you can break it into an n1 and n2 factorization, then you can turn that n squared algorithm into n times n1 plus n2. So you can say if it was evenly split, you can square root one of your n's, which is really nice. This is n times the square root n. And you can apply this recursively to get order n log n. I did not do the analysis. I just trust that they're correct in that. So this works well for N that has small prime factorizations. Powers of 2 are absolutely ideal because you can just keep splitting it down the middle. Perfect. So for that reason, in my benchmarks, I do powers of 2 and then pure primes. So the best and absolute worst case scenarios for my FFTs are the ones I'm going to benchmark. So a bit more about benchmarking issues, just how I had to engineer this thing. BLAST does not have a single API. There's no flexi FFT. There's no common wrapper for them. I actually have to write the FFT calls myself for each of the implementations and then compile against each of them separately. Some FFT libraries use plans, notably FFTW and Sleef. If you've never heard of Sleef, it's a pretty fast way to do a bunch of things. And they work on powers of 2 FFTs. They have varying dimension support. I did 1, 2, and 3. I won't get into 2 and 3 here. And they all use different underlying algorithms, so you need to test a variety of problem sizes. And they all have varying thread support. I don't actually get into the thread support here either. So I just told you this. I did not use NanoBench here. I used Google Benchmark, which by comparison absolutely sucks. NanoBench is more powerful, it's more accurate, it's faster, it gives you more statistics. I just like it better. If you're using the C++ world and you're doing micro benchmarks, NanoBench is the best. It counts instruction counts, and you can get it down to things that only require 1 instruction you can benchmark. So just much, much better. These are the implementations I looked at. You probably never heard of most of them. You probably heard of FFTW and MKL. For various reasons, I at some point made a list of benchmarks on all of these, and so that's what I'm using for this talk. Duck is something made by Martin Reinicke, one of our kind of collaborators for FNUFT. Pocket is also made by him. It's sort of the predecessor to Duck. It's just there for, and you can compile these in source. Like you don't need to link them separately. Sleef, like I mentioned, this is a vectorized library to do like functions, basically, but they decided to add FFTs to it for some reason. KISS, which is a very simple FFT that is absolutely crap, and FFTW and MKL. KISS doesn't claim to be good. It's not their fault.
Well, it stands for keep it simple, stupid?
Yeah, I assume this is, using the common engineering principle of keep it simple, stupid. So we'll get into the results real quick. So my plots aren't quite as nice. These are sort of rehashed. So solid lines, this is, I've one, y-axis. Time per grid point in nanoseconds. So it's normalized by the number of points. So if this is an order n algorithm, it would just be completely flat, but it's not. It's n log n, so it should have a slight upslope. I did it on a log scale because the difference in speeds are a factor of 100. And the solid lines are the implementations for powers of 2 problem sizes. And the dotted lines are the nearest prime to that power of 2. So you can see, let's take the MKL line and let's go over here to a nice little 10,000 grid points. We're about, a little over 1.1 nanoseconds. And up here, we're 10 nanoseconds. So it's literally a factor of 10 slower to do a prime FFT versus a power of 2 FFT. So they're actually, you could do tricks where you use something like FNUFT and spread over a nice even powered thing to get faster implementations on this. But the takeaway is don't do FFTs of things of prime sizes unless you absolutely have to. If you can change your problem size very slightly, just leave off that last point, whatever, you'll get much, 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 much better performance. Yeah, KISS is the brown one. You see it's like 5-6 times slower than Sleef does very well. But FFTW is the fastest. It is the fastest Fourier transform in the West. That's what it stands for. And it is, yeah. And it is. I mean, they're still holding true to their name. MKL is not even competitive here on the, this is Rome nodes. There's a question? I thought I saw a hand.
Sure. Well, I'll ask.
Yeah.
Is there some reason why you can't always fudge it up to the next power of 2?
I mean, you have the data set you have.
So it won't solve the problem if you fudge it up?
You could lie to it, yeah. You could interpolate.
It solves a different problem. That's the
But
it solves a slightly different problem.
Can you take that solution and apply it to your original problem? I don't really understand how it's applied. Okay.
Sometimes, not always, I think is, you have to be careful with this stuff. And like I said, I'm not an FFT expert, so I would trust Alex's explanation on this. Yes, Brian?
I don't even see a dashed line for KISS FFT. Is that because it's off the plot or it like never completed?
That's a good question. Yes, I think I removed it. I did remove it. That's actually true. I had to take it off because it did this. I think it took 10 to the 4th nanoseconds per point. And there's 10 to the 6 points. So, yeah, it was the bottleneck for my benchmarks, and so I had to remove it because it made the plot unusable. Same here. Here, this is an Ice Lake node. Much like the BLAST-LAPACK situation, MKL actually performs very well. MKL is the orange line. FFTW, though, is in a deadlock. Like, you don't really need to micro-benchmark. The problem with FFTW is FFTW requires a plan. You have to make this plan. Making this plan takes time, and then you need to keep this plan. The plan is based on the problem size. So if I'm doing a 1,000,000-point FFT, I have to make that plan once. And actually, the old bottleneck is why I only go up to 10 to the 6th. I used to go up to 10 to the 8th, is because making the plans for FFTs was taking hours, literal hours, which can be fine if it pays off. But when not making a plan with MKL takes literally 0 time, and you get the same performance, then who cares? Just use MKL. But if making the plan isn't a problem, then FFTW is still the fastest, or like deadlock with MKL. Yes?
Which type of planning were you using?
This was the measure. Because the estimate, if you use FFTW estimate, it's actually about half the speed for a lot of these. So when you're doing FFTW, if you're doing an FFT like hundreds or thousands or millions of times, use the measure flag. There's also like an overkill flag, I forget what it's called. That can literally take days, but you can save it. So if you really want the absolute best for a machine, you can save the plan and use it for a huge run. Like if you have a simulation that's going to take months, this can save you days.
Sorry, do you know what's the plan doing? Is it like go to the computer specifics, or is it like?
Sorry, do I know what is doing?
The plan, like what are the parameters of the plan?
Oh, they're calculating these so-called twiddle factors, and they're also doing trying to optimize how they block their algorithm. Because like I said, this is based on basically doing a prime factorization. So I assume what they're doing is factorizing it and deciding because they keep subdividing the problem, and what is the optimum way to subdivide the problem evenly. But I haven't actually ever looked at the code, so that's me talking out of my, but anyway, MKL, FFTW, deadlock on Ice Lakes, and FFTW wins again on the Genoas. It's still the fastest. Duck performs reasonably well, and so does Leaf. Pocket's old, we don't care about it, and don't use KISS. MKL actually performs very, very badly on the Genoas. Like this is actually like 30% or something. It's real bad, at least for small transforms. My conclusion is use FFTW3 unless you have a very good reason not to. There are lots of good reasons not to use FFTW. One is the planning issue. MKL doesn't require plans. Another is if you're packaging FFTW, there are lots of caveats, which I will talk about in a bit with my work on FNUFT. FFTW is GPL licensed. If you package it as part of your code, You're supposed to package your code also as GPL, but a lot of us don't want to do that. There's lots of reasons that you don't want to do that, or it's complicated. There's a lot of decisions. There's another issue, but I'll talk about it in a minute. So I have no multi-threaded results. It's not because I didn't do them. It's because I couldn't get quality plots in time. I do have some measurements. I have an anecdote about multi-threading, and that is that FFTW plans are not thread safe. Working on FNUFT, this actually can cause a lot of headaches. Like if you're building a library that other people are going to use, and you're calling FFTW in a multi-threaded context, you have no way of knowing if another library is using FFTW at the same time, and they're also making plans. So the only thing that's thread safe in FFTW is the execute. Anything that adds or removes plans or messes with the so-called wisdom, the static state, is not thread safe. So what FFTW does is when it builds a plan, it stores it statically in memory somewhere, and then if something else tries to build a plan at the same time, that routine itself is not thread safe. We had to write this issue has come up like 3 or 4 times in FNUFT where we've had to engineer fixes for it. We think we finally have one. And the answer is we have a lock that you have to pass in from an external user to pass in a lock that says, I promise that FFTW, if I'm running it, will be using this lock. It's complicated. It's a nightmare. MKL plans, there are none. Thread safe by default. Duck, no plans, thread safe by default. So you do have to be careful with these planning things. This cost me, I don't know, probably a week's worth of my life, at least. And not the most fun week. It was, and that's it for my talk, actually. That's all. If there are any questions, I work on a lot of things. Benchmarking-wise, I do have a lot of random knowledge about how to make things fast. So if there's any questions, let me know. My doohickey is stuck. Okay. Thank you. Hi, Chris.
Very cool talk.
Thanks,
Okay.
Chris.
You're welcome. Let's say instead of doing these large matrix operations, I instead decide to work in Cartesian space. All of my stuff is 3 vectors. Is it still better just to write my own?
What do you mean 3 vectors?
Or like just 3 coordinates, so you have x, y, z for all of your points.
Oh, yeah, using...
Let's say it's all Cartesian coordinates and quaternions.
I mean, if you're only doing mat-vec operations, it should be fine-ish. It depends. If it's a bottleneck, then you should start considering SIMDifying your own thing or turning it into a nice big blast op. But for GemV, the time complexity is so low that it's not as much of a problem writing your own. And I think if we look at the size 8 GemVs, maybe that would give us a hint if I'm correct in this. So size 8, this is the closest to Cartesians we're going to get. There's about twice as much work. My blast is this purple one, and we see I'm colorblind, so this is maybe not okay. This one, it's tiny. Actually, don't write your own.
Okay.
You could actually probably get by doing a bunch of GemVs, and it would be faster.
Can I chime in? There are a lot of people have written small
Yes, there's.
libraries, and you can find those.
That might be even a better bet. There are small matrix and vector sort of BLAS implementations that are different and quite fast.
And you should also make sure that if you write a little loop for things, then the n, the loop size, which is 3, is known by the compiler.
On the other hand, eigenBLAS is competitive. So if you're using eigen, it will vectorize it nicely, much nicer than the naive loop. So yeah, you can use one of those or eigenBLAS. They both, or not eigenBLAS, just eigen, and that should work quite well in the C++ space at least. Yes.
So I know that when you're using eigen, there are some additional flags you can pass that will
De-eigenuse blasts?
Yeah. Did you look at what the effect of those is using various things?
I did not try that. I suspect that it will just cost you slightly more time than just calling it directly.
Okay.
Though I think they say that Eigen has an option that says, in some cases, I want to use, rather than doing all the matrix math myself and compiling the code for it, I'll just call BLAS. And then you can use whatever BLAS implementation you want. And that often will be faster. But I'm not sure. I didn't benchmark it. So I don't have the details on how that actually works out. Because there's memory copies and things. So for small ones, it might be an issue. For bigger ones, I doubt it's as much because the time complexity is so big. Anything else?
Well, could I make a suggestion? I mean, this is a really cool snapshot of kind of the state of the art on libraries right now, on state of the art hardware right now. It's all going to, in 2 years or 5 years, it'll all change. But is there a way we could sort of have a Flatiron benchmark suite that we run? Could this be formalized and sort of run every year or something? It's very useful.
This plot requires me to run 2 commands. So
okay, well, right.
And it automatically, all you would need to do is change the versions of the libraries it points to and change the scripts very slightly to run on modern hardware. I'll be, like my FFT benchmarks and my special function benchmarks, I'll be adding this to my collection of things that I benchmark. And then, yeah, in 2 years, it should be very easy. This is very easy to run. You don't have to really do anything.
And you're going to put that in a GitHub repository?
I'll be adding it to the GitHub repositories, yeah. I might end up just merging all 3 of them into one. There's a bunch of data viz problems that come up when you're benchmarking literally thousands of things that I should talk to some of our data viz people about, like maybe building a nice little web interface so that you can, because one of my other projects is special function benchmarks. So let's say you want to, you calculate Bessel functions. Which Bessel function implementation should I use? The difference in speeds of those things is like literally order thousands. So it actually can matter quite a bit. And in some other things, it doesn't matter at all. So, but how many special functions are there? And then you have like special versions with new indices and all these things that turn into a combinatoric problem. And so visualizing that data effectively is quite hard. Okay? Thanks, everyone.